Good morning, dear students. Welcome to another session of microwave and antenna. So, in previous session, we discussed regarding beam area or the beam solid angle. So, with respect to that, we will be solving a few problems. Okay. Even I require the concept which we had discussed over in this part. So, we had in previous sessions, right? We had seen how we can obtain the half power beam width and first null beam width. So here if this pattern is given, E of theta is equal to cos square of theta. How do you identify the half power beam width? This equation is evaluated to E max divided by square root of 2. And then you obtain the value of theta and you take twice of theta, which will give you the half power beam width. That is what you have done. So this concept is also required. So same similar kind of concept was applied over here also. So yesterday we discussed regarding the power density, which is power flow power flow through the unit area. Therefore, power density's SI unit is watt per meter square. So therefore, the unit of power density is watt per meter square. Therefore, if you want to identify the total power, you refer to the power theorem, which implies that you have to take the double integration of the power density with respect to the elemental surface area. So this will give you the total power, and this is power theorem defined in terms of power density. So this we had discussed yesterday. Then we discussed regarding what is meant by power theorem, and we discussed regarding what is the elemental surface area. So here, remember elemental surface area sometimes denoted as dA or it is ds. So this elemental surface area is given by r square sine theta d theta d phi, which is obtained by multiplying these two sides of the small elemental area. So this is what we had referred, and from this we had obtained another parameter, that is this is equal to r square d omega. We had obtained even this parameter where d omega is what? It is a solid angle. In this case, it is a elemental solid angle. So we discussed regarding beam area or beam solid angle, which is given by omega A, which is given by omega A. And if I want to obtain the beam area or beam solid angle of any particular pattern, then I should know what is its power pattern. I should normalize it and then utilize it in utilize it in this equation. So this is what, since I want the total beam area, right? I know what is the elemental solid angle. I want the beam solid angle. So it is with respect to the normalized power pattern. So therefore what I do, the the beam solid angle is given by the double integration of normalized power pattern with respect to the solid angle. Now yesterday we saw that the range of solid angle will be in the range of 0 to 4 pi, because 4 pi is the maximum solid angle which is subtended by the sphere. No other element will subtend any angle which is greater than 4 pi. Maximum is 4 pi. But omega is actually constituted of two angles, that is, it is with respect to theta and it with respect to omega. So therefore, these limits I can replace it in that form. That is, phi is in the range of 0 to 2 pi and theta is in the range of 0 to pi. And in this side, we substitute for d omega. D omega is sine theta, d theta, d phi. So how did you obtain this? This we obtained because of this elemental surface area, which is r square sine theta d theta d phi, which I replace as r square d omega. So d omega is nothing but this parameter, sine theta d phi. So it is basically multiplication of two angle parameters. It is multiplication of two angle parameters. So this is what we had discussed. So this equation, what we have is called the exact equation, and we can obtain even the beam area or beam solid angle if I know the half power beam width. So in order to obtain that, we can utilize this equation. We can utilize this equation where omega A, that is the beam area or beam solid angle, is the product of the half power beam widths along theta and phi direction respectively. So it is a product of the half power beam widths in theta and phi directions respectively. So this is actually the approximate equation. This is termed as approximate equation. And yesterday we also saw that what is one steradian. So solid angle unit, SI unit is steradian. Steradian. But one steradian is equal to 1 radian square. But what is 1 radian? It is 180 divided by pi. So 180 divided by pi, its square, that value when you simplify, you will get the square degrees representation. So this is how you obtain, you can convert steradian to radian and then radian to square degrees. So these are the two equations what we have to look out for when we are solving the problems. So this is the exact equation and this is the approximate equation. So let us try to solve one of the problems. So you can note down this. Find the number of square degrees in the solid angle omega on a spherical surface that is between theta equal to 20 degrees and theta equal to 40 degrees and between phi equal to 30 degrees and phi equal to 70 degrees. In this case, right, what they are asking is they are asking us to identify the square degree representation for the solid angle. So solid angle has to be represented in terms of the square degrees. So now here, and what is the information they have given? They have given that we have to identify it for the area which is falling within this range. That is, theta is in the range of 10 to 40 degrees and phi is in the range of 30 to 70 degrees. So this is one way of specifying the problem. Another way of specifying the same problem is if you just observe for theta, right? Theta is actually what? Elevation angle. It is elevation angle. So elevation angle can also be specified in terms of latitude. In terms of latitude, that is 70 degrees and 50 degrees north latitude. 70 degrees and 50 degrees north latitude. So if you just take 70 minus, difference between 90 degrees and 70 degrees, you will get the first angle, and 90 degrees and 50 degrees, you get the next angle. So since this is specified in north latitude, right, you have to subtract it from 90 degrees. So that is when you consider the earth, right, what you're specifying is you're specifying that you are moving north by 70 degrees and you are moving north by 50 degrees. So in terms of theta, these are the two angles. These are the two angles. So here what we are doing is, so it will be like you start from this point and you move up to this point. So if I move to some point, so if I just consider this, say this is 70 degrees. And if I take up to this point, say this is 50 degrees. So that is this part. That is this part in terms of theta. So if you're specifying in terms of latitude, right, what is happening is this is, say if I consider this from 0 to 90 degrees, generally we measure it from the elevation angle. That is 0 degrees is here and 90 degrees is here. What you're specifying is 70 degrees at this point and 50 degrees at this point. That is these 2 points. So if I consider, if I have to estimate it with respect to theta, right, when we have specified it in terms of the north latitude, we have to take angle from here, that is theta is at, so this is 70 degrees from north latitude, but with respect to theta it will be 90 minus 70, which is actually 20 degrees with respect to theta. And similarly the other value what they have specified that 50 degrees towards north latitude. So when I specify, so this is 50 degrees with respect to this point. So but with respect to theta, when you are measuring, it is 90 minus 50, which is 40 degrees. So that's why this angle is represented. So either we can specify it in this form or we can specify this in the latitude form. But when you consider the other one, right, it will be with respect to 30 degrees and 70 degrees east longitude. East longitude. This one is like along the equator what you're specifying. Along the equator what you're specifying, and your starting point is from east. So here when you consider phi, no need to convert this value whatever is specified. So in this case, phi will be 30 degrees and 70 degrees respectively. But when we are specifying north latitude, right? So there we have to convert this. So now how this value is actually represented. So this is a part of the sphere, that is that is we are considering, we are the this small elemental area information is given in terms of angle. It is given in terms of information with respect to the angle. So here from here one point is at 20 degrees and the other point is at 40 degrees. So I got the theta values and the phi values from here. When I move, one is 30 degrees and the other part is at 70 degrees. So this information he has given. So now I have to estimate what is this area. What is this area? From that area, I'll be able to estimate what is the solid angle. Now here you can see that the elemental surface area for this one is given by dA, which is equal to r square sine theta d theta d phi. And this d omega I need to estimate. I need to estimate d omega, which is sine theta d phi, because that is as per the problem what they have specified. In problem, what they want to identify, they want to identify what is the solid angle which is subtended by this small area. What is the solid angle which is subtended by this small area, which is actually given by this d omega, which is actually equal to sine theta d phi. So now I need to estimate sine theta d phi. Now in these cases, right, what is d theta and d phi? These are the small elemental changes in theta and phi angles respectively. So now we'll come back to the problem. So here what we have, theta is at 20 degrees and 40 degrees. So if I happen to measure the theta, right? So at 20 degrees and 40 degrees are the 2 points where this area is located. And what are the latitude values? So if I represent it in this form, right? So what is this specifying is this is at 30 degrees, this is at 70 degrees. So that is what we have now. Now here what happens is directly I cannot consider the theta values for the calculation. Here I know what is d phi. So here if you just observe, here if you just observe what we have, the difference between these two is 40 degrees. So which is nothing but the d phi value. Sometimes we note it even as delta phi. So 40 degrees is the difference between these two azimuth angles, which is 40 degrees, which is nothing but the d phi or the delta phi value. Now, what is d theta value? D theta value is the difference between these two angles, 40 and 20. So difference between these two angles is, difference between these two is 20 degrees. So what this identifies, this is nothing but it is d theta, or sometimes denoted as delta theta. Okay. Now I want to identify what is this value. So this one I can identify. It is nothing but r d theta phi. But what is this one? As per a previous discussion, it is r sine theta d phi. Now for simplicity, what we assume is since r value is not specified, we'll consider it to be unity. So therefore, what happens is this side will be reduced to sine theta d phi, and this side will be reduced to d theta. Now what I want the solid angle which is subtended by this entire area, and this is actually given by the multiplication of these two sides, sine theta d phi multiplied with d theta. Now I know what is d phi. D phi is 40 degrees, and what is d theta? D theta is 20 degrees. So this is in terms of degrees. Now what is the theta value over here? This theta value is obtained as the median value between these two. It is obtained as the median value between these two. The median value of 40 and 20 degrees is 30 degrees. The median value of 40 and 20 degrees is 30 degrees. Therefore, this theta turns out to be 30 degrees. So when I substitute this theta value, right, sine 30 into what we had, say we had 40 degrees and we had 20 degrees. Now remember, whenever you're doing multiplication and other stuff, right, with respect to angles, these angles should be represented in their SI unit form. So therefore, what you have to do is you have to convert this one into radian and even 20 degrees into radian, and then you multiply and obtain the overall result. Don't multiply this value, whatever you are getting over here, with respect to the angles keeping in degrees. So you should not do that when you are multiplying the angles. If you're just multiplying the angles, that is not a problem. But what you have is, along with the angle, you have the other parameter over there. Therefore, you should be careful when you are performing that operation. So here, what did we do? We referred to sine theta, d theta, and d phi. D phi is 40 degrees, d theta is 20 degrees. But what is the theta value in the sine parameter? It is the median of these two. So which is 30 degrees, which is 30 degrees. So now substitute these values in sine theta, d theta, d phi. So it is sine theta into 40 degrees, and d theta is 20 degrees. So when you multiply these, when you multiply these, you will obtain the solid angle which is subtended by the small elemental area. So here we can see that this value is turned down to 20 degrees, and this one, when I make the simplifications, I'll get a result of 20 degrees. So therefore, when I multiply these two, So that is elemental area, elemental angle of theta and elemental angle of phi. I'll get the solid angle which is subtended by that sphere. So it is, so indirectly the multiplication what we are speaking. So here sine theta d theta, sine theta d theta d phi. So when I obtain that overall result, I'll get this value. So this is coming around 400 square degrees. It is coming around 400 square degrees. So there is another way of obtaining the solid angle. Now that is overall solid angle which is subtended by this. So how do I obtain that? So I can obtain it with the help of the equation. Now since in this case I got to know that d omega is what it is, sine theta, d theta and d phi. So I know what is the elemental angle with respect to this. Now I want to identify what is the overall angle. So what I do is I take the overall, in order to identify the overall solid angle, I double integrate this d omega. I double integrate this d omega. So when I do that, what I get is I get this parameter. So it is omega, which is equal to double integration of the elemental angle. So this, since we are considering R to be unity. So if I obtain this one, if I simplify this, I'll be getting results in this form. And here you can see that phi is in the range of 0 to 2 pi and theta is in the range of 0 to pi. This is general form. But now you know that this elemental area is falling within theta of 20 degrees and 40 degrees and phi in the range of 30 degrees and 70 degrees. So directly you can refer to these angles and substitute in the equation. So here what you have done, you can observe omega is equal to integration of phi is equal to 30 to 70 degrees and integration of theta equal to 20 to 40 degrees and sine theta d theta d phi. When you simplify this, you will obtain the overall result. And again, remember here what you're doing is you are multiplying this value with the angle parameter. So remember, when you're performing this operation, you have to convert this one into radians. So if you don't convert this one into radians, you will end up in wrong results. Okay, so you should be careful when you're performing this operation. So this one, you need to convert it into as radians. So here when you convert this, you get omega, which is equal to 0.121 steradians. 0.121 steradians, which is actually equivalent to 0.121 radian square. But what is the answer required? It is required in terms of square degrees. So now previously we had seen that how we obtain square degrees. So this one is 1 radian into 0.121 radian. So that is how I can write it. So indirectly, what you can do is, if you multiply this parameter, if you multiply 0.121 with the 180 divided by pi the whole square, you will get answer in terms of square degrees. You multiply 0.121 with 180 divided by pi the whole square, you will get the answer in terms of square degrees. So when you convert that, what we'll get? We'll get nearly 397.22 square degrees. So this is why I'm getting this lesser than the previous cases, because here you are considering the exact representation. You're considering the exact represent. You are using the exact equation over here. But what in the next case, what you're doing is you are considering the approximate equation, wherein you are considering sine theta, d theta, d phi. So that is what is happening. So this is how you obtain the radiation, the beam area or beam solid angle. So we'll consider another example. An antenna has a field pattern which is given by E theta is equal to cos square theta and theta is in the range of 0 to 90 degrees. Find the beam area for this pattern. Now here there are two methods of identifying the beam area. So one we had seen that beam area is obtained by here beam area is obtained by the exact equation which is termed as the double integration of normalized power pattern into sine theta d theta d phi. So this is the exact equation, and you can obtain it from the approximate equation wherein you try to identify the half power beam widths of the given pattern and multiply both the half power patterns and obtain the beam area. So we'll try to see what's the difference between these two. So in this one, we know what is the field pattern, but I have to obtain the power pattern. Power pattern is obtained using this equation where the power pattern is equal to square of the field pattern. It is equal to square of the field pattern. And in integration, right, I should use the normalized power pattern. Now, if you just observe this parameter, right, if you just try to measure the values, its value will be ranging from 0 to 1. Its value will be ranging from 0 to 1. So if you just observe, it is already normalized field pattern. So if I take the square of the field pattern, I'll get the normalized power pattern. I'll be getting the normalized power pattern. So if I take square of this directly, that is E square, I'll be getting the normalized power pattern. So in this case, I am using the pattern which is provided in order to obtain the beam area. Therefore, omega A is double integrated with respect to E square, since this has to be the normalized power. So, and power is square of the field pattern. E square sine theta d theta d phi. Now here the angle is specifically given that it is in the range, theta is in the range of 0 to pi by 2. So therefore what we do, angle omega is equal to, we substitute the limits, phi is equal to 0 to 2 pi and theta is equal to 0 to pi by 2, and e square theta is nothing but cos square raised to square. So it is cos raised to 4 theta into sine theta d theta d phi. So now once we integrate this, you either you go for the substitution method or you can use the alpha and gamma and beta functions. You can use the gamma and beta functions. So whichever you are comfortable, you can go ahead with that. So in this case, we have referred to the substitution method wherein we substitute cos theta is equal to x. Therefore, minus of sine theta d theta will be replaced with dx, and the limits will be if theta is 0. If theta is 0 in this case, then x will be 1, and if theta is equal to pi by 2, x will be 0. So when we substitute this limit and simplify, when we substitute these limits and simplify for the beam area, we get 2 pi by 5, which is 1.26 steradians. 2 pi by 5, which is 1.26 steradians. So this is the beam area or beam solid angle which is subtended by this radiation pattern. This is a beam solid angle which is subtended by this radiation pattern. Now, what about the approximate equation? So here what we can do is, since we know what is the field pattern, in previous problem, right, that is in previous sessions, we had identified what is the half power beam width for this cos square theta pattern. So if in order to identify that, we had equated E theta equal to 1 by square root of 2. So for which we had obtained theta equal to 33 degrees, for which we had obtained this value. And half power beam width was equivalent to 2 times theta value, which is 66 degrees. Now here, since only one direction the field pattern is given. So in the other direction, what we assume is we assume that the half power beam width is also same in the other direction. So here we have got for theta value. So what we do is we assume that phi HP is also similar and it is equal to 66 degrees. So now when we multiply these two values, that is theta HP and phi HV, we get the approximate value for the beam area. So which turns out around 4356 square degrees. And when we convert it into steradians, right? So if I have to convert square degrees into steradians, you have to multiply this one with pi divided by 180 its square. You have to multiply this parameter with pi divided by 180 its square. So when you perform that, you will get 1.33 steradians. 1.33 steradians. So here you can see that this is 1.26 by using the exact equation. By using the approximate equation, you are getting it as 1.33. So it is because of these approximations what we are doing, that is one part. And apart from that, what happens is in this approximate equation, right, we neglect the minor lobe effect. We had studied, right, we had major lobe, minor lobe, then side lobes. So here side lobe effects are also considered. So because of that, you have this difference in beam area. Here it is lesser because you are using the exact representation of the pattern. Here you are approximating these parameters and you are utilizing it. So this is with respect to beam area. So continuing with the next parameter, that is radiation intensity, or sometimes just termed as intensity. So how is this intensity defined? This is represented with capital U. This is represented with capital U. So radiation intensity, it is defined as the radiated power per unit solid angle. It is defined as the radiated power per unit solid angle, and this radiated power is considered from the antenna. So in previous case, what we discussed, we had discussed regarding the power density. So for this one, it is power flow through unit area. Through unit area. Now in this case, that is the radiation intensity, we are considering the power flow through unit solid angle. So in this one, what happens is the unit of this one will be watt per steradian. It will be watt per steradian. Now, if I know the radiation pattern, then I can obtain the normalized power pattern. So which is given by this equation. If I know either the radiation intensity or the power density, I'll be able to obtain the normalized power pattern, which is given by U divided by U max, where this is the radiation intensity, U is the radiation intensity, or S divided by S max, where S is the power density. S is the power density. Or even we term it as the Poynting vector, which is nothing but the cross product of E and H. So it is nothing but the power density value. So here radiation intensity is given in this form, and it is defined as power radiated from an antenna per unit solid angle. So here we had seen that small elemental surface area is given by r square sine theta d theta d phi. When I simplify this, what I'll have, ds is equal to r square d omega. It is equal to r square d omega. So therefore, if you just observe, what we have is we have ds, which is given by r square d omega. So when we consider only d omega, it is actually given by ds divided by r square. ds divided by r square. So if I take ds divided this r square this side, what is left? It is left only with this parameter, which is equal to sine theta d theta. It is d phi. Sine theta d theta d phi. So therefore, this is what is represented over here. That is d omega is ds divided by r square, which is sine theta d theta d phi. So now, previously what we had obtained the total power by referring to the power theorem. It is integration of S or P value, which is the power density with respect to small elemental surface area. Now I can, if I know the radiation pattern, if I know the radiation intensity, then also I can obtain the total power by taking double integration of this one. But here it will be with respect to d omega. It will be with respect to d omega. Here it is with respect to ds. So which is, in which ds is what? It is r square sine theta d phi. But if I know the intensity, right, then I refer this double integration with respect to d omega. And what is d omega? D omega is sine theta d phi. So this is power theorem in terms of power density, and this is power theorem in terms of radiation intensity. So as we had again here, theta and phi limits have to be identified. If you're considering the full sphere, phi will be ranging from 0 to 2 pi and theta will be ranging from 0 to pi. And if you consider half sphere, phi range will not alter. Phi will be from 0 to 2 pi, whereas theta will be ranging from 0 to pi by 2. Now, if you're considering the intensity, radiation intensity, just remember it is sine theta d phi. But if you're considering the power density, then it will be power density into r square sine theta d phi. So these are the two definitions of power theorem. That is theorem defined in terms of power density and defined in terms of radiation intensity. So this is with respect to radiation intensity. So next we have the discussion pertaining to isotropic antenna. Now in previous this thing what we discussed, we had power density and radiation intensity discussion, where power density is power flow per unit area and radiation intensity is power flow per unit solid angle. Now, whenever we consider an antenna at the center of the sphere, so we imagine that there is a sphere surrounding this antenna, and if I happen to measure the value of the either the radiation or the radiation intensity or the power density, and throughout the surface of the sphere, so if I move at any point on the sphere, right, if I happen to measure a constant value, so at one particular distance I have considered, and on that I am moving around on the surface of the sphere, so in which the antenna is assumed to be present at the center of the sphere. So if I measure and if all the measurements turn out to be identical, that is all the values lead to P naught and U naught. So if any antenna provides you such kind of radiation, we call that antenna as isotropic antenna. So basically isotropic antenna is an ideal antenna, or we can consider it as the reference antenna. So if an antenna radiates equally in all directions, if it radiates equally in all directions, then at a given distance, if you measure at any point either the power density or the radiation intensity, you will get the same value throughout that surface of the antenna. So such an antenna is termed as isotropic antenna. So this is termed as isotropic antenna. What will be the total power radiated by such kind of antenna? Isotropic antenna. What is the total power radiated by such kind of antenna? So in this case, what we have is we refer to the power theorem. We refer to the power theorem. What this specifies? Now, if I assume that P naught is the power density which is emitted by the isotropic antenna which is under consideration. So if I apply to this power theorem, it is double integration of P naught dot ds. Now, as we know that P naught will be a constant value because it will be same if I measure at this point, that is all these points are at a distance d, r. They are at a distance r. So if I take at r, here also it will be P naught. So throughout the surface, if I measure, it is a constant. So therefore, this P naught is a constant. So I take this constant parameter outside. I take this constant parameter outside and I take the double integration of ds. Now, what is a double integration of ds? So if you substitute the values, right? If I substitute the values, so if I substitute the value for phi is in the range of 0 to 2 pi, and theta is in the range of 0 to pi. Now, in previous discussion also, we had observed that the radiation pattern for the isotropic antenna will be a sphere. Sorry. So next we have radiation patterns. Already we have discussed this. So under that we had discussed what is meant by power patterns and what is meant by field patterns. So just a recap of the previous session. We can wind the session up. So what is the power pattern? It is nothing but the plot of power density, with respect to theta or with respect to phi, if you're considering the two-dimensional representation. Now, if you are using the power density values as it is, that is, you're not normalizing them or you're not converting them to dB values. So then what we do is we refer to such pattern as absolute power pattern, since I'm using the absolute value of the power is being radiated by the antenna. Now, suppose if I normalize this, so how do I normalize the value? I take all the p values and divide it by the maximum p value, that is the power density value. So this will give me what? This will give me the normalized power pattern. And if I plot the normalized power pattern versus theta or versus phi, I get what is known as normalized power pattern representation, which is termed as relative power pattern, since you are plotting all the power values relative to the maximum power value. Now, if you take this value and convert it into dB, that is 10 log P, or you take 10 log P by PM, that is the normalized value. And if you plot it with respect to theta or phi, you get the dB plot. You get the dB plot. So similarly, we have a radiation pattern in which what changes happen is you plot U, that is radiation intensity. You have intensity pattern in which you plot intensity, radiation intensity versus theta or phi, in which we get the absolute intensity pattern. And if I take the normalized value of this one, U divided by U max, I'll get the normalized radiation pattern. And if I plot this one with respect to theta or phi, I get relative intensity pattern. And if I take the log of this one, even for this case, it is 10 log of U or 10 log of U by UM. You will get the dB plot. Now next you have the field pattern. So field pattern is nothing but plot of electric field versus theta or phi. So this will give you the the absolute field pattern. Now, if you plot E divided by EM, if you plot this one with respect to theta and phi, you get the normalized field pattern, or it is also termed as relative field pattern. And lastly, if you take the log of this one, that is 10 log of this, you will get 20 log of this, you will get the field pattern in terms of dB. Field patterns in terms of dB. So lastly, what is meant by phase patterns? Phase pattern is nothing but the plotting of the phase difference between the transmitted and received signals with respect to the antennas. So if you plot that, you will get what is known as phase patterns. Then based on these values, right, we have another representation, that is isotropic isotropic pattern. So what is isotropic pattern? As I mentioned, this is the pattern which is relevant to the isotropic antenna. And since isotropic antenna radiates equally in all direction, it will be spherical in shape in three-dimensional representation, and it will be circular in its representation in two-dimension. So if you observe a sphere from front, it appears as though it is a circle. Say if I observe the sun, it will be appearing as though it is just a circle. But we know that it is spherical in shape. In three dimension, it is spherical, but in two dimension, when I represent, it is circle in nature. Now, what is directional pattern? So this one is refers to the unidirectional antennas. That is antennas which are radiating in one particular direction. In the other direction, they are not radiating. So in one particular direction they are radiating, and in the other particular direction they are not radiating. So such antennas we classify as unidirectional antenna, and patterns for those are classified as directional pattern. Now, what is meant by omnidirectional? Now, what happens is these kind of patterns are obtained from antennas which have uh, uh, which have which are directional in one of the planes, and which are omnidirectional in the other plane. Say for example, if I consider in theta plane, right, in theta plane they might be directional, that is they might be say radiating more in one of the directions, but in the other directions it might appear as though it is omnidirectional. That is, if I consider say a pattern which is donut shaped pattern. So this is how it will appear, donut shape pattern. So if you just observe this one, right? If you just observe this, what you have is, if I observe it in a two-dimensional representation, here you can see that it is circular in nature. Its radiation pattern, that is, if I observe from top, it is circular in nature. If I slice this and observe in two-dimensional in these directions, that is, say this is the phi plane, or this is one, say one is theta plane and one is phi plane. In one, this thing in phi plane, it is directional. It is directional, but in this one, you cannot make out in which direction it is emitting, but it is emitting uniformly. So such kind of patterns we classify as omnidirectional pattern. Such kind of patterns we classify as omnidirectional pattern. So this is all for today. We'll meet in the next session. Thank you.